In the last video, we talk about how seasons on Earth are not caused by how close Earth is to the sun in its orbit. And we also hint at the fact that it's actually caused by the tilt of the Earth. And so in this video, I want to show you how the tilt of the Earth causes the seasons to happen. So let's draw. So I'm going to try to draw as many diagrams as possible here, because at least for my brain, they help me visualize what's actually going on. So we can imagine a top view first. So let's have a top view. That is the sun right over there. And let me draw Earth's orbit. So Earth's orbit maybe looks something like that. Let me draw it almost. It is almost circular, so I'll draw it as something that's pretty close to a circle right over here. And I'm going to draw Earth at different points in its orbit, and I'm going to try to depict the tilt of its rotational axis. And obviously, this is not drawn anywhere near close to scale. Earth is much further away from the sun and much, much smaller than the sun as well. So I'll draw the Earth at that point. And at this point, the Earth will be tilted away from the sun. So Earth's tilt does not change if you think about the direction, or at least over the course of a year, if we think about relatively small periods of time. It does not change relative to the direction that it's pointing at in the universe. And we'll talk about that in a second. So let's say right over here, we are pointed away from the sun. So we're up and out of this page. So we are up and out. So if I wanted to put some perspective on an arrow, it would be up and, actually it would be more like up and out of this page. So that's the direction if you were to come straight out of the North Pole. And if you were to go straight out of the South Pole, you would go below that circle right over there. And if I wanted to draw the same position, but if we're looking sideways along the plane, the orbital plane or the plane of Earth's orbit. So if we're looking at from that direction, so let me do it this way. If we're looking at directly sideways, this is the sun right over here. This is the sun. That is the sun. And this is Earth at that position. This is Earth at that position. This is Earth right over there. If I were to kind of draw an arrow pointing straight out of the North Pole, if I were to draw an arrow coming straight out of the North Pole, it would look something like this. It would look something like this. So this arrow and this arrow, they are both popping straight out of the North Pole. And so when we talk about the tilt of the Earth, we're talking about the tilt of its orbital axis, kind of this pole that could go straight between the South Pole and the North Pole. The angle between that and a pole that would actually be at a 90-degree angle or perpendicular to the plane of its orbit. And so compared to if it was just straight up and down relative to the plane of the orbit. So this right here is the angle of Earth's tilt. Let me draw that a little bit bigger just so it becomes a little bit clearer. So if this is the plane of the orbit, we're looking sideways along the plane of the orbit. And this is Earth right over here. So this is Earth. My best attempt to draw a circle. That is Earth. Earth does not rotate. Its axis of rotation is not perpendicular to the plane of the orbit. So this is how Earth would orbit. This is how Earth would rotate if it was. Earth rotates. Earth's rotational axis is at an angle to that vertical relative to the plane of its orbit, I guess you could say it. It rotates at an angle like this. So this would be the North Pole. That is the South Pole. This is the South Pole. And so it rotates. It rotates like this. And that angle relative to being vertical with respect to the orbital plane, this angle right here for Earth right now is 23.4 degrees. 23.4 degrees. And if we're talking about relatively short periods of time, like our lifespans, that is constant. But it is actually changing over long periods of time. That is changing between, and these are rough numbers, it is changing between 22.1 degrees and 24.5 degrees, if my sources are correct. But that gives a rough estimate of what it's changing between. But I want to make it clear, this is not happening overnight. The period before it to go from roughly a 22-degree angle to a 24.5-degree angle and back to a 22-degree angle is 41,000 years. 41,000 41,000 years. And this long-term change in the tilt, this might play into some of the long-term climatic change. Maybe it might contribute on some level to some of the ice ages that have formed over Earth's past. But for the sake of thinking about our annual seasons, you don't have to worry too much, or you don't have to worry at all really about this variation. You really just have to know that it is tilted. And right now it is tilted at an angle of 23.4 degrees. Now, you might say, okay, I understand what the tilt is, but how does that change the seasons in either the northern or the southern hemisphere? And to do that, I'm going to imagine the Earth when the northern hemisphere is most tilted away from the sun, and when it is most tilted towards the sun. So remember, this tilt, the direction this arrow points into relative to the rest of the universe, if we assume that this tilt is at 23.4%, it's not changing throughout the year. But depending on where it is in the orbit, it's either going to be tilting away from the sun, as it is in this example right over here, or it will be tilting towards the sun. Or it would be tilting towards the sun. I'll do the towards the sun in this magenta color. Or it would be tilting towards the sun. So 6 months later, when the Earth is over here, it's going to, relative to the rest of the universe, it will be tilted in that same direction. It will be tilted in that same direction, up and up, out of this page and to the right. So out of this page, and to the right again, just like it was over here. But now that it's on the other side of the sun, that makes it tilt a little bit more towards the sun. If I were to draw it right over here, it is now tilted. It is now tilted towards the sun. It is now tilted towards the sun. And what I want to do is, what I want to think about is how much sunlight will different parts of the planet receive. And I'll focus on the northern hemisphere, but you can make a similar argument for the southern hemisphere. I want to think about how much sunlight they receive when it's tilted away or tilted towards the sun. And so let's think about those two situations. So first of all, let's think about this situation here where we are tilted away from the sun. So let me zoom in a little bit. So this is the situation where we're tilted away from the sun. So if this is the vertical, so let me draw it. I could actually just use this diagram, but let me make it. So we're tilted away from the sun like this. We'll do this in a different color. So if we have an arrow coming straight out of the North Pole, it would look like this. If we have an arrow coming straight out of the North Pole, and we are rotating around like that. So we're out of the page on the left-hand side and then into the page on the right-hand side. And so we're rotating towards the east constantly. So this arrow is in the direction of the east. So when we are at this point in Earth's orbit, and actually let me copy and paste this, and I'm going to use the same exact diagram for the different seasons. So let me copy, and then let me paste this exact diagram. I'll do it over here for two different points. So when we are here in Earth's orbit, where is the sunlight coming from? Well, it's going to be coming from the left, at least the way I've drawn the diagram right over here. So the sunlight is coming from the left. Sunlight is coming from the left. Sunlight is coming from the left in this situation. And so if you think about it, what half of the Earth is being, or what part of the Earth is being lit by sunlight? Or what part of the Earth is in daylight? The way I've drawn it right over here. Well, the part that is facing the sun. So all of this right over here is going to be in daylight. As we rotate, whatever part of the surface of the Earth enters into this yellow part right over here will be in daylight. But let's think about what's happening at different parts of the Earth. So let me draw the equator, which separates our northern and southern hemispheres. So this is the equator. This is the equator. And then let me go into the northern hemisphere. And I want to show you why, when the North Pole is pointed away from the sun, why this is our winter. So when we're pointed away from the sun, well, if we go to the Arctic Circle, so let me go right over here. Let me go to some point in the Arctic Circle. As the Earth rotates every 24 hours, this point on the globe will just rotate around just like that. It will just keep rotating around just like that. And so my question is, that point in the Arctic Circle, as it rotates, will it ever see sunlight? Well, no, it will never see sunlight because the North Pole is tilted away from the sun. So what I'm shading here in purple, that part of the Earth, when it's completely tilted away, will never see sunlight. or at least it won't see sunlight while it's tilted away, while it's in this position, or in this position in the orbit. Never, I won't say never, because once it becomes summer, they will be able to see it. So they not, no sunlight, no day, I guess you could say, no daylight. No daylight. If you go to slightly more southern latitudes, so let's say you go over here. So maybe that's the latitude of something like, I don't know, New York or San Francisco or something like that. Let's think about what it would see as the Earth rotates every 24 hours. So this would be daylight, 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 then nighttime, 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 nighttime. This is now going behind the globe. Nighttime, 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 daylight, 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 daylight. So if you just compare this, so let me do the daylight in orange. So daylight is in orange. And then nighttime I will do in this bluish purplish color. So nighttime over here. So if you go to really northern latitudes, like the Arctic Circle, they don't get any daylight when we're tilted away from the Earth. And if we go to slightly still northern latitudes, but not as north as the Arctic Circle, it does get daylight, but it gets a lot less daylight. It spends a lot less time in the daylight than in the nighttime. So notice, if you compare the 20, if you say that this circumference represents the positions over 24 hours, it spends much less time in the daylight than it does in the nighttime. So because while the northern hemisphere is tilted away from the Earth, it is the latitudes in the northern hemisphere are getting less daylight. So they're getting less daylight. They're also getting less energy from the sun, and so that's what leads to winter, or it just being generally colder. And to see what happens in the summer, let's just go the other side. So now we're going to the other side of our orbit around the sun. This is going to be 6 months later. And notice, the actual direction relative to the rest of the universe has not changed. We're still pointed in that same direction. We still have a 23.4 degree tilt relative to, I guess, being straight up and down. But now once we're over here, the light from the sun is going to be coming from the right. The light from the sun is going to be coming from the right. Just like that. And now, if on this diagram at least, this is the side of the Earth that is going to be getting the sunlight. And let me draw the equator again, or my best attempt to draw the equator. I'll draw the equator in that same color, actually, in that green color. So this is separates the northern and the southern hemisphere. And now let's think about the Arctic Circle. So let's say I'm sitting here in the Arctic Circle. As the day goes on, as 24 hours go around, I'll keep rotating around here. But notice, the whole time I am inside of the sun. I'm getting no nighttime. There is no night in the Arctic Circle while we are tilted towards the sun. And if we still do that fairly northern latitude, but not as far as the Arctic Circle, maybe in San Francisco or New York or something like that. If we go to that latitude, notice how much time we spend in the sun. So maybe we just enter. So this is right at sunrise. And then as the day goes on, we are in sunlight, 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 sunlight. Then we hit sunset. Then we hit nighttime, nighttime. Then we hit nighttime. And then we get sunrise again. And so when you look at the amount of time that something in the northern hemisphere spends in the daylight versus sunlight, you'll see it spends a lot more time in the daylight when the northern hemisphere is tilted towards the sun. So this is more day, less night. So it is getting more energy from the sun. So when it's tilted towards the sun, it is getting more energy from the sun. So things will generally be warmer. And so you are now talking about summer. You are now talking about summer in the northern hemisphere. And the arguments for the southern hemisphere are identical. You could even play it right over here. When the northern hemisphere is tilted away from the sun, then the southern hemisphere is tilted towards the sun. And so, for example, the South Pole will have all daylight and no nighttime. And southern latitudes will have more daylight than nighttime. And so the south will have summer. So this is summer in the south, in the southern hemisphere, and it's winter in the north. And then down here, the southern hemisphere is pointed away from the sun. So this is winter. This is winter in the southern hemisphere. And you might be saying, hey, Sal, what about, you haven't talked a lot about spring and fall. Well, let's think about it. Well, if we're talking about the northern hemisphere, this over here we decided was winter in the northern hemisphere. And we are going to rotate around the sun. And at some point, we're going to get over here. We're going to get over here. And then, because of this tilt, we aren't pointed away or towards the sun. We're kind of pointed, I guess, sideways relative to the direction of the sun. But this doesn't favor one hemisphere over the other. So when we're over here and this will actually be the spring now. When we're in the spring, both hemispheres are getting the equal amount of daylight and sunlight. Or for a given latitude above or below the equator, they're getting the same amount. And the same thing is true over here when we get to, so this is the spring, this is the summer in the northern hemisphere. Now this will be the fall in the northern hemisphere. And once again, we're tilted in this direction. And so it's not the northern hemisphere isn't tilted away or towards the sun. And so both hemispheres are going to get the same amount of radiation from the sun. So you really see the extremes in the winters and the summers. Now, one thing I do want to make clear, and I started off with just the length of day and nighttime, because frankly, that's maybe a little bit, or at least in my brain, a little bit easier to visualize. But that by itself does not account for all of the difference between summer and winter. Another cause, and actually this is probably the biggest cause, is if you think about the total amount of sun. So let's talk about the northern hemisphere winter. And let's say there's a certain amount of sunlight that is reaching the Earth. So there is a certain amount of sunlight that is reaching the Earth. So this is the total amount of sunlight that's reaching the Earth at any point in time. At any point in time, you see that much more of that is hitting the southern hemisphere than the northern hemisphere here. All of these, if you imagine it, all of these rays right over here are hitting the southern hemisphere. So a majority of the rays are hitting the southern hemisphere, and much fewer are hitting the northern hemisphere. So actually a smaller amount of the radiation period at even a given period in time, not even talking about the amount of time you're facing the sun, but at any given moment in time, more energy is hitting the southern hemisphere than the northern. And the opposite is true when the tilt is then towards the sun. Now a disproportionate amount of the sun's energy, is hitting the northern hemisphere. So if you draw if you just think that this is all of the energy from the sun, most of it, all of these rays up here are hitting the northern hemisphere, and only these down here are hitting the southern hemisphere. And on top of that, what makes it even more extreme is that the actual angle that and of course this is to some degree is due to the fact of where the angle of the sun relative to the horizon, or where you are on Earth. But even more than that, if you are on, let's say that this is the land. Let's say this is the land. And we're talking about the winter in the northern hemisphere. So let's say you're talking about, let's say we're up over here at this northern latitude, and this is just and we're just looking at the sun here. And over here, you can see even when we are closest to the sun is not directly overhead. When we're closest to the sun still is pretty low on the horizon. So maybe right over here, when we're closest to the sun in the winter, the sun might be right over here. But if you look at that same latitude in the summer, when it is closest to the sun, the sun is more close to being directly overhead. It still won't be directly overhead because we're still at a relatively northern latitude, but the sun is going to be much higher. The sun is going to be much higher in the sky. And these are all related to each other. It's kind of connected with this idea that more energy is hitting one hemisphere or the other. But also, when you have I guess you could say, a steeper angle from the rays of the sun with the Earth, it's actually going to be dissipated less by the atmosphere. And let me just make it clear how this is. So in the summer, so let's say that that's the land. And let's say that, let me draw the atmosphere. I'll draw the atmosphere in white. So all of this area right over here, this is the atmosphere. And obviously, there's not a hard boundary for the atmosphere, but let's just say this is the densest part of the atmosphere. In the summer, when the sun is higher in the sky, the rays from the sun are dissipated by less atmosphere. So they have to get through this much atmosphere, and they're bounced off, and they heat some of that atmosphere and they're absorbed before they get to the ground. In the winter, when the sun is lower in the sky, so maybe the sun is out here. Let me draw it a little bit. So when the sun is lower in the sky, relative to this point, you see that the rays of sunlight have to travel through a lot more atmosphere. So they get dissipated much more before they get to this point on the planet. So all in all, it is the tilt that is causing the changes in the season, but it's causing it for multiple reasons. One is when you're tilted, we'll say when you're tilted towards the sun, you are getting more absolute hours of daylight. Not only are you getting more absolute hours of daylight, but at any given moment, most or more of the sun's total rays that are hitting the Earth are hitting the northern hemisphere as opposed to the southern hemisphere. And the stuff that's hitting the places that have summer, it has to go through less atmosphere, so it gets dissipated less.